Hello, and welcome to my video on magnetism. In this video, I will discuss the basics of magnetism, the concept of the magnetic field, and the 4 different right-hand rules often associated with the magnetic field. My name is Atirth, and without further ado, let's begin our investigation of magnetism. The basics, that is. Okay. So before I dive into magnetism, I need to discuss the magnet. So a magnet is a metal conducting bar that's composed of 2 primary parts, the North Pole and the South Pole. Now, the interesting thing about the North and South Pole is that if you have a North Pole of one magnet if you have the North Pole of one magnet next to the South Pole of another magnet, a force will be exerted on these 2 magnets, and this force is attractive, and by Newton's third law they have the same magnitude. So there's a force F exerted towards, let's call this magnet 1, let's call this magnet 2. So there's a force F exerted on magnet 1 towards magnet 2, and likewise there's a force F being a force with the same magnitude, exerted on magnet 2 in the direction of magnet 1. This is an attractive force. And notice that this is the case when the North and the South Pole are next to each other. Alrighty, so now let's look at what happens if we have a North and a North Pole next to each other, or a South and a South Pole next to each other. In other words, like poles. So suppose you have this scenario over here. You have a North and a South, and then you have a South and a North. And again, let's call this a magnet 1 and magnet 2. You'll find that if you experiment with this, you'll find that there's still going to be forces exerted on these 2 magnets, but this time this force is repulsive. In other words, even though it's the same magnitude, it's going to push the magnets away from each other, whereas before the force pushed the magnets towards each other. So again, we'd have a force F, but instead it'll be directed outward for magnet 1, a force F directed outward for magnet 2. And this would still be the case if instead of the South poles facing each other, we had the North poles facing each other like this. In other words, when you have like poles facing each other, there's going to be a repulsive force exerted on the magnets. And when you have opposite poles facing each other, you're going to have an attractive force exerted on these magnets. So, much like a positive and negative charge on you'll notice that this is much like positive and negative charges when dealing with electrostatics, except now we're talking about poles. I'll get to this in a minute, but I just want to let you know, in case you were wondering, the definition of a North Pole is the pole where magnetic field lines are radiated outwards from the pole. And the magnetic South Pole is the pole where the magnetic field lines are radiated inwards, or converge inwards. Radiated, I guess, isn't the right word. And I'll explain more about what field lines means and all that soon. But I just want to let you know that this is the definition. The field lines exit the North and enter the South. And I'll let you know what that means shortly. Before I move on to discussing field lines, there is one thing I wanted to mention. It's not going to be on your tests or any of such thing, but it's just interesting to know. And from history, this has normally been a confusing topic for a lot of students. And that is the distinction between the geographic and the magnetic North Pole, or the geographic and magnetic South Pole. So, suppose we take a look at the Earth, which is the planet that we live on, in case you were wondering. And this is the Earth's axis at 23.5 degrees with respect to the ecliptic. This is our North Pole, this is our South Pole, as any atlas would tell you. Now imagine yourself in the 1500s or so, where compasses were becoming the new popular navigating tool. Now compasses are interesting tools in that they are normally some container that's filled with some sort of fluid, normally water, and it has, in addition to these cardinal directions, it has a magnetized needle on the inside. So it would tell you, say, this is what it looked like. So this is a magnetized needle that's freely floats in the water. And if you're in the northern hemisphere, well, this magnetized needle points to the part of the compass that says north. So naturally, people gave the pole way at the highest point on the northern hemisphere, or the North Pole, the geographic North Pole. They gave it the name North Pole because that's what the compass pointed to. So geographically, this was what was called the North Pole. Now, I want you to think about this for a second. Here we have a magnetized bit of iron or whatever other metal that they were using, and it was pointing north in the northern hemisphere, meaning this magnet here was attracted to this part right here. Obviously, the Earth is a bar magnet, or could be thought of as a bar magnet due to its interior. So it has some magnetic pole here and some magnetic pole here. So if this pole here, the north pole of the magnet here, pointed to this pole of the Earth, since we know opposite poles attract, this pole has to be the magnetic south pole, and therefore this pole has to be the magnetic north pole. Now this has nothing to do with anything that is going to be on the AP Physics C test, but I just wanted to put that in there because a lot of times it's a confusing concept, and I'm not sure if I clarified it or made it even more confusing. Probably the latter, but I hope this helps with the clarification of this topic. So now I'm going to move on to a discussion of fields and field lines. So let's talk about fields. So what are fields? Well, fields are, or rather a more appropriate name would be a force field. In this case, we're talking about the magnetic force field, also abbreviated as the B field. Now, this might sound like something straight out of, a science fiction book, but a magnetic force field, or the B field, is a field where if you were to place a charged particle inside this field, a force would be exerted on that charged particle. So, kind of like the electric field with a charged particle as well. So, basically, if you say you have these field lines going this way. All right, and say you have a negative charge over here. Because this is a negative charge, in this magnetic force field, or the B field, there will be a force exerted on this charge, and soon we'll be able to not only find out what the magnitude of that force is, we'll be able to tell the direction that the force is exerted on it as well. But from this diagram right here, you should take away that this charge, the charge negative Q, will have a force exerted on it by the B field. And that's the definition of the B field, or any force field for that fact. It's a field where if you were to place, in this case, a charged particle, a force would be exerted on that charged particle. So you'll notice before I erase that line, you notice that I represented this field with arrows. And that's one of the most convenient and one of the conventional ways of representing a magnetic field. Suppose we have a magnet, say a horseshoe magnet, which is just a bar magnet, curved such that its north and south poles face each other. So that would look something like this. Something like that. Let's call this the North Pole, let's call this the South Pole. And you'll remember from what I said earlier that field lines come out of the North Pole, they're radiated out of the North Pole and re-enter through the South Pole. So that means they'll radiate out from here and they'll go to the South Pole like so. Perhaps in a different color it'll be easier to visualize because I'm not sure how clear all this black is. Let's see. I'm going to use it in blue because that's the only other color I have. So you'll see that the B field is shown in these blue arrows, and these arrows are indeed called magnetic field lines. They're just a convenient geometrical way of representing the magnetic field, and it's an easy and neat way to kind of wrap our heads around this abstract concept of a force field. So, before, I'd like to add one more thing about the magnetic field lines. Much like electric field lines, magnetic field lines, you can find out, you can find out their uniformity, so to speak, or a measure of how uniform they are based on their density, the density of the lines. So suppose we have a magnetic force field, or a magnetic field rather, that looks like this. I'm just going to assume that I drew this uniformly. So because the density in this region is constant, we therefore assume that the magnetic field in this region is constant. And that's how we represent the uniformity of a B field. If the field lines are drawn have a uniform density or a constant density in a given region, then the magnetic field in that same region is thought to be constant. So let's take a look at another example. Suppose we have this. So far pretty uniform. I'm not sure this will show up on the video. Okay, it was pretty uniform up until here, and then here it kind of got more and more spaced out in this region right here. So what that tells us is this magnetic field exists in this entire region over here. It exists in this entire region right here, but in this subset of the region, it's uniform, and here it's not uniform. So I just wanted to put that out there so someone could see what a non-uniform magnetic field could look like, or one example of a non-uniform magnetic field. Oops. Okay. So now, as promised, I will be giving you or walking you through the formulas for finding the force exerted on a charged particle in a magnetic field. Now, I know I've said this before, but I just like to stress it again. Only and only a charged particle will have a force exerted on it if it's in a magnetic field. Not just some regular, like if I have this neutral marker and there's a magnetic field in this room, there would be no force exerted on this marker because it's not charged. On the other hand, suppose I had a 2 Coulomb particle somewhere, and I had it in the room, and there was the same magnetic field here. A force would be exerted on that particle because it's charged. So a magnetic field, again, only exerts a force on charged particles. That's important, so don't forget it. Please don't forget it. So I'll now run you through some of the formulas for finding the force exerted on a charged particle. And a lot of times we will assume constant B fields, but if we don't, then I'll show you how to work out those problems as well. You'll need to know how to do integrals. So the first formula is, suppose you have a B field. Oops, I don't like this marker. It's not very dark. Here it is. Suppose you have a uniform B field going in this direction. Okay, and you have a charged particle that's moving. Oh, yes, I forgot to mention. A force is only exerted on a charged particle that's moving. It has to be moving, meaning velocity has to be non-zero. It can be in either direction, but it has to be moving. Non-zero velocity. Add that to the thing not to forget. Charged particle that is moving is the only type of particle that will have a force exerted on it by a magnetic field. Okay, don't forget it. So suppose we have this and it's moving, say, let's see, where would it move? Let's say it's moving upward. Okay. So how would you find the force exerted on this charged particle with charge Q? That's a charge Q, by the way. Well, the formula to use for this one is force is equal to Q, which is the charge of the particle, V, force is a vector, velocity is a vector, crossed with the magnitude of the magnetic field. So force is equal to QV cross B, or QVB sine theta, where theta is the angle between V and B. So let's look at this example here. I have a red. So let's look at this example here. We have velocity going in this direction, and we have the magnetic field going in this direction. So the angle between them is 90 degrees. If it's 90 degrees, sine of 90, as you should know, is 1. So that reduces our formula down to just QVB. So we know the Q of the particle, we know the velocity that the particle is moving in, and if we know the strength of the B field, we should be able to find the magnitude of the force exerted on this particle. Now that's only part of the equation, because we know force is a vector, and a vector is any quantity that has both direction and magnitude, and this formula helps us find the magnitude. But now we need to talk about the direction. Uh-oh, things are falling. So, sorry about that. So suppose here's where we use what's called a right-hand rule, and this will be your first of 4 right-hand rules. 4. I initially thought it was 3, but there's 4. So the first right-hand rule says, oh, and I should probably write the formula here. The first rule says, and again, there are many ways to do this, but this is my version of this first right-hand rule. You point your index finger on your right hand. Don't use your left hand, because if you do, you'll lose points, and I'm telling you from experience. It's called a right-hand rule for a reason. So use the index finger on your right hand and point that in the direction of V. So in this case, it's going to be going upward. Then you use your middle finger and you point that in the direction of the B field. So V is going here, and B is going upward, and B is going this way. Whichever direction the thumb points in is the direction of the force exerted on this particle. So let's look at this again. We have velocity of the charged particle going upward. We have the B field pointing this direction. So by the right-hand rule, my thumb is pointing into the board. So the direction of so we know the force is given by, its magnitude is given by QVB. And its direction would be into the page. And one way to represent that would be through this mark. It's a circle with the cross through it. So that's how you find direction and magnitude for a moving charged particle through a magnetic field. However, a lot of times it's not just one charged particle that's moving, it's a whole slew of charges that are moving in what's called a current. So let's go back to the original B field that we have. Oh, I don't like this marker. And let's say we have a wire carrying a current I. This is B, by the way, going outward. And it's carrying a current I in this direction. Well, how could we solve that? We know current is equal to dq dt, which is the rate of change is basically how many charges or how much charge passes through a segment of wire in a certain time. The change in the charge passing through a certain segment of wire over a certain time, taken at the infinitesimal. So we know that's the case, and we know the force is equal to QV cross V. We know V is also the same as dx dt or dl dt for a segment of wire of length L. So Q d, let's call that dl dt cross b. Okay, but we also know dq dt is I. So we can write this as dq dt L cross B. And mind you, L is a vector because it's a displacement, position, whichever vector works best with your understanding. So this we have dq dt times L cross B. dq dt is I. So this formula comes down to I, the current passing through the segment of wire, times length, times the B field. That should be capital, by the way. So this is our second important formula that we need to know. Let me actually make a list of all the formulas that we need to know right here so we don't forget. Let's see. I don't remember which one was a good marker. Yeah, it's this one. So here's a list of all the formulas. Force is equal to Q V cross B. This is your first one. Your second one, the one we just found together, was force is equal to I L cross B. And the right-hand rule for this formula works in the same way. We point our index finger of the right hand in the direction of the current. So in this example, in this case. And again, we point the middle finger, which I'm not going to pull up on its own for obvious reasons, in the direction of the B field. So I goes here, B goes there, and our thumb points in the direction of the force exerted on this piece of wire carrying a current I. So I, B, and again, F points into the board. Now that's not too surprising because our original particle was moving in a velocity in the same direction, and now we have a whole slew of particles moving in this direction. So force would still be exerted in the same direction, and its magnitude would be given by this. So that's our second law for finding the force exerted on either a singular charge or a whole slew of charges in a segment of wire or a current. Okie doke. Now, so those are the two formulas you needed to know. Force is equal to QV cross B and force is equal to IL cross B, where L and B and V and B are vectors. Okay, so now that brings me to my my last two right-hand rules. And these two right-hand rules are a little different because they aren't necessarily used for finding magnitudes. They're just used for finding directions. So one of the fundamental discoveries of studies in electromagnetism is that a current-carrying wire produces its own magnetic field. So suppose we have a wire with current I going in this direction. This is the wire, and that line I used to represent the current. Now you'll remember earlier that a magnetic field exerts a force on a moving charged particle. That was important fact number 1. This is important fact number 2. A moving current in a wire will produce its own magnetic field. So how are you going to find the direction of this magnetic field? Fear not, here comes the third right-hand rule to our rescue. So what you do is you point your thumb of your right hand, again, this is called the right-hand rule for your reason. You use your right hand, so you point your thumb of your right hand in the direction of the current, and you're going to curl your other fingers of your hand around, and that curl will tell you the direction of the magnetic field. In this example, I'm going to point my thumb in the direction of the current. So I goes in this direction, my fingers curl in this direction. At the bottom they'll go into the page, and at the top they'll come out of the page. So, let's see. How am I going to draw this? Oops, that is not supposed to happen. Okay, so these black rings that I drew show the direction of the magnetic field created by this moving current in the wire. Because we pointed our thumb in this way, it goes inward at the bottom here and comes out at the top. So it's moving clockwise, perpendicular to the wire, at perpendicular, I guess, cross sections of the wire. So that's how you use this third right-hand rule, sorry. You point your thumb of your right hand in the direction of the current and wrap your fingers around it. Let's look at another example. Suppose we have a wire with current coming out of the page, which we represent by a dot. Remember, we use a cross to represent going into the page and a dot to represent coming out of the page. And we want to find the direction of the magnetic field due to the current in this wire. Well, we know current's coming out of the page, so we curl our fingers around it, and we see that it goes in a counterclockwise direction. So we see that it goes like this. And for those of you who missed it, the right hand's like this. Point your thumb in the direction of the current out of the page, and this curls around in the counterclockwise direction. So that's our third right-hand rule. Okay, so I will now be talking about the fourth right-hand rule. Pardon the little jump in the video. So in this one, our third right-hand rule talked about how to find the direction of a magnetic field given a straight moving current. Well, now suppose we have a curly current, for lack of a better term. And to demonstrate this right-hand rule, I'm going to use a solenoid, which is like a spring or a slinky. I'm going to redraw this because it's not the best diagram. So suppose we have a solenoid. Okay, and these loops are going in and out of the page, and they're not in the plane of the page. They're perpendicular to the plane of the page. Like if I took a slinky and kept it like that, just for an idea of reference. And suppose our current was going in the loop like this. That is, it's going from this side, it's going here, and it's going around like that. Okay, so what is the direction of the magnetic field inside of the solenoid? Well, to do that, let's identify what the direction of the magnetic field would be at the tips of both the top and the bottom of the solenoid. At the top of the solenoid, which is a ring coming out in this direction like this, the current is traveling outward like this. So if the current is traveling outward like this, then the magnetic field for this one tiny instant would be, take it out here, and it curls inward like this. So it curls inward like this. I'm going to use a red marker to draw that. At this tiny section, the magnetic field goes in like that. And that's true for each of these sections. So we can actually draw one giant red arrow right here. Now, if you do the same at the bottom, current is going inward, and you'll realize that the magnetic field for that tiny section inward also points in this direction. So it goes like this. And current, if you look at current, say pieces of wire on either of the front lateral sides of the solenoid, they'll cancel each other out, the magnetic fields. So the only one we really care about are the top and the bottom. And we notice that the current, the magnetic field produced inside seems to travel in this direction. So, and we know the current is going into the page at the bottom and out of the page at the top. It's going into the page at the bottom and coming out of the page at the top. The magnetic field seems to point in this direction. That's our fourth right-hand rule. If we curl our fingers in the direction of the current, in this case it's going in at the bottom, coming out at the top, our thumb will point in the direction of the magnetic field inside of the solenoid. So that's our fourth right-hand rule. Not to be confused with the third one, where current is straight and we want to find the magnetic field due to a straight path of current. Here we're finding the magnetic field due to a curved path of current. So those are our four right-hand rules. And for concluding this video, I will just go through some practice problems in finding force exerted on a particle due to a magnetic field or on a charged particle, be it moving or singular or a current. So suppose we have a magnetic field with magnitude, say 10 Teslas, which is the SI unit for a magnetic field. So, and suppose we have a charge with, say, 10 coulombs, and it's moving at 10 meters per second. What is the magnitude of the force exerted on this? And they're all perpendicular to each other. So this and this are at 90 degrees to each other. So in that case, we know force is equal to QVB. In this case, Q is equal to 10, V is equal to 10, V is equal to 10, is equal to 1,000 newtons. Now, these aren't realistic numbers, but I'm using them for the sake of example. And if we want to find the direction, well, let's say this is the setup. Suppose we had a magnetic field that's going into the page and it's uniform. Like that. And suppose so it's going into the page like this. And suppose we had a particle moving at a velocity to the right. With a velocity v, moving to the right. Well, in that case, we know v is moving to the right, force is pointing inward, so that means my thumb points upward. So the force exerted on this particle, oh, I have a green marker. The force exerted on this charge will be upward, and we'll have that magnitude of 1,000 newtons. So this is an example of how to solve a problem like this. Now, talking about current, suppose we have a magnetic field again with 10 Teslas of magnitude, a current with 10 amps, and a length of 10 meters. Again, not ideal, not realistic numbers, but easy for calculations. We want to find, and this are perpendicular to each other, so sine of theta is 1. So then we know force is just given by ILB. I is equal to 10, L is equal to 10, B is equal to 10. This comes out to, again, 1,000 newtons. And if we want to find the direction, well, suppose again we had, I really shouldn't have erased it the first time. Suppose we have this magnetic field where the magnetic field lines are going into the page again, and this is our bit of current. It's going in this direction. So let's use our right-hand rule to find the direction of the force exerted on this particle, on this wire, sorry. So again, we have the length going in this direction and the B field going into, so force would be upward. Now bear in mind, these are ideal situations where the angle between, in this case, the length and the magnetic field are 90, and in the previous example, the velocity and the magnetic field were 90. If that's not the case, then you can't just use ILB or QVB to find the magnitude, although the right-hand rule still works. You have to supplement it with ILB or QVB sine theta, where theta represents the angle between V and B or L and B, depending on which of these problems you're working on. So don't forget to do that. And that brings us to the end of the video.